morning, my YouTube viewers. It is Crystal here. In this video, what I'm going to do is I'm going to use R to perform an ARIMA on the Nile dataset. So an ARIMA is a time series prediction. It's a time series prediction, and you can do it in R or Python, but I'm going to do it in R. And the thing about R, the difference between R and Python is the ARIMA function is inbuilt in the R program, whereas in Python, because Python is a general purpose language, you have to use a library to use the ARIMA function. So R is a program that has been written specifically for statisticians. So it has a lot of inbuilt programs in it, or inbuilt functions in it, that you won't see in Python, that you will only be able to get in Python if you import a library such as stats models. But we're going to go ahead and go over this ARIMA, and we're just going to use inbuilt libraries in R. So the Nile is an inbuilt data set in R, and it covers the flow of the Nile measurements from 1871 to 1970. And if you watched my previous video, then you will know that the flow of the Nile has been decreasing over the past century. And then we proved that by creating a scatter plot which showed that it was gradually decreasing. And then we also created a box plot to show that the values in the second half century of the measurements were less than the values in the first half century of the measurements. So with all that being said, we're going to go ahead and start working on this ARIMA so you can see how you can do an ARIMA in R. The first thing that we're going to do is we're going to create a Jupyter notebook. And you can, what I found out recently is you can program R into a Jupyter notebook by typing into your browser https://collab.research.google.com/notebook create equals true and language equals R. So if you type that into your browser, then that will call up a Jupyter notebook that allows you to write a program in R. So we're going to call up the Nile dataset, which is an inbuilt dataset in R. So we're going to find out that the class of the Nile is TS, which means it's a time series. And then we're going to find out the structure of the Nile is 100 elements from 1871 to 1970, and it's a time series. So the start of the Nile is 1871, number 1 element, and the end of the Nile is 1970, number 1 of the element. So we're going to view the Nile dataset, and you can see that the Nile dataset is a time series dataset with 100 elements in it. We're going to, just in case you didn't know, we're going to check the length of the Nile. The length of the Nile is 100. Now what we're going to do is we're going to create a scatter plot of the Nile. And again, we're going to be using inbuilt functions to create this scatter plot. And again, one of the nice things about is R has the capacity to do plotting program built into the into the R programming language. whereas Python does not have the ability to do that. If you want to do that in Python, you have to import a library such as Matplotlib or PyPlot. So that's one advantage that R has over Python. And another thing is data scientists are still using R. And I was watching a YouTube video, and the YouTube video said that R is still more popular than Python. But all the information that I gathered is that data scientists need to know how to use R and Python. So if you don't know how to use R, this is a good starting video to teach you how to use R. So in this particular scatter plot, it also has a linear model in it. So we're going to put a regression line in it. And the regression line is going to be red, and we're going to put a grid in it as well. And then after we've typed in the code and we have run it, you can see you've got the scatter plot, and you can see that as time goes on, the measurements of Nile just very slowly decrease, very mildly decrease, but you can actually see a decrease, and the regression line shows you that there is actually a decrease. So now we're going to plot the Nile measurements decrease every year. So we're going to plot that as well. And you can see this is what the Nile measurements look like on a line plot. And again, you can see that the measurements are just very mildly decrease over the years. So now we're going to create a box plot of the Nile. Again, so what we've done is we've created a scatter plot, we've created a line plot, and we've created a box plot. So those are 3 plots that you can do in R, but you can do a lot more plots in R as well, but that's just 3 that we're doing in this video. So you can see the values of the measurements are from below 600 to above 1400 with an IQR, that's an interquartile range of around 900. And Q1 is around 800, Q2 is around 900, Q3 is over 1,000, and Q4 is 1,400. So what we're going to do is we're just going to convert the Nile data set into a standard data frame. So R also has a data frame function that's inbuilt into the program that you can use. And again, if you want to do that in Python, you have to import a library to do that, such as Pandas. So in this data frame, we're going to have a year and a measure. And then the next thing we're going to do is we're going to break down the data set into decades. So DF $decade is the floor, brackets DF $year divided by 10 times 10. And then here is the data frame broken down into decades, but we're not really going to use that. But I used it in another program, and I decided to go ahead and leave it in. And so what we're going to do now is we're going to drop the last row of the Nile data set. And the reason why or the data frame, the reason why we're going to drop the last row of the data frame is because when you do a box plot for the decade, you get a box plot for 1970s, which is a really tiny box plot because there's only one cell in 1970. So I decided to just go ahead and drop the last cell in the data frame. So DF no last becomes head brackets df comma -1 df no less. So we've dropped the last cell, so now you only have 99 cells. And so what we're going to do is we're going to create a box plot for the decades, even though we're not really going to use it in the ARIMA. I used it in a previous program or previous video, and I decided to go ahead and leave it in here for this video, just in case you want to know how to make a box plot for the decade. So you can see here we've got the measurements per decade, and there's no box plot for 1970. And the reason why there's no box plot for 1970 is because there was only one cell in 1970, and it was just a really tiny box plot. It wasn't relevant, so I removed it. So you can see when you look at the measurements, you can see that over the decades, the measurements have slowly decreased. The measurements in 1870 are much higher than the measurements in 1960s. So the decreased flow of the Nile is partly linked to global warming. Human factors such as overuse, dam construction, irrigation, and water management policies also affect the decreased flow of the Nile. Now what we're going to do is we're going to start working on the ARIMA. So we're going to calculate the PDQ. And the PDQ are the three components that we have to calculate in the ARIMA. So the first thing we're going to do is we're going to break our training set down into a training set and a testing set. And so we've got the code right here for how to break it down into a training set and a testing set that you can pause the video and see how to do that. And then so our training set has 80 elements, and our testing set has 20 elements. And now what we're going to do is we're going to set up our grid. And so P values becomes 0 to 8, D values become 0 to 3, and Q values become 0 to 8. Best score becomes infinite, and the best config becomes null. And so basically what you're doing is you're setting it up. So you're initializing the best score and the best config. So now we're going to set up a series of for loops. And so what I'll do is you can pause the video so you can see the for loops that we've set up. So for P and P values, for D and D values, for Q and Q values. And then your order becomes C, and C is letting you know that you're setting up a list of some sort. But a list in R is different from a list in Python. So you're setting up a sort of a list. You're setting up a list of elements containing PDQ. And then you're going to try catch. It's the same as Python's try except or try exempt. So we're going to fit the ARIMA model on train X, and the order equals order. So in ahead, it becomes linked X test. Pred, that's your prediction, equals predict fit dot in dot ahead equals in head. And another great thing about R is, like, if you want to do machine learning or time series analysis and you want to make predictions, then if you want to do that in Python, then what you have to do is you have to import libraries. And the reason why is because Python is a general purpose language, whereas R was designed just for statistics. And so time series was considered a part of statistics a long time before it was considered a part of machine learning. So that's why they put time series as an inbuilt function in R. So we're going to calculate the noise, which is your RMSE, which is a root mean squared error, becomes the square root of the mean of test x minus the prediction squared. And then we're going to track the best model. So if the RMSE is less than best score becomes RMSE, best config equals order. And then cat sprint F equals ARIMA, and then DDD brackets RMSE equals percentage 3F next line. And then you're going to put the PDQ and the RMSE in there. And cat sprint F is a type kind of a print function. And R will accept some Python commands, so if you want to put print in there, you can. But cat sprint F is the correct code to use. And then so if you have an error, it says skip failed fits. And then so at the end, so what it does, it iterates through the for loop through all of the elements of the order, which is your PDQ, and then after it has iterated through all of that, then it prints out the best score being the ARIMA PDQ and the RMSE. And then so you can see here that I've run the program, and the best score was 6,0,7, and the RMSE was 114.475. So that was the best arrangement that the program could find. So now we're going to set up the ARIMA, and we're going to put in the ARIMA the 607, and the RMSE was a comparison of the test set and the predictions on the test set, but we're not going to be able to calculate the RMSE on the ARIMA, and the reason why is because we're going to make a prediction on the next 10 years. We're going to make a prediction on the next 10 years. And so since we don't know what the next 10 years are going to be unless we actually go onto the internet and find out what the measurements were from 1970 to 1980, we're not going to know it. So since we're not going to know it, we're not going to be able to fit the RMSE in there. But in order for us to do the ARIMA for the next 10 years, we're going to say fit becomes ARIMA brackets Nile, comma order equals C brackets 6,0,7 brackets. And then we're going to inspect the model, so we're going to fit it. And then so when we run the ARIMA, then you have the ARIMA, you have the coefficients, and you have the AIC, you have the log likelihood is -66.72, and the AIC is 1283. And the AIC is another metric in time series analysis that determines the goodness of fit of the model that you used. So now we're going to plot it. So we're going to forecast for the next 10 years. Pred becomes predict brackets fit, comma n dot ahead equals 10. So that's 10 years. And then print pred. And then so we're going to plot the forecast. We're going to plot a line plot. And then we're going to, which is blue, a line plot of the Nile and the prediction, which is black and blue. And then we're going to plot two red lines, being the prediction plus 2 times the standard error, and the prediction minus 2 times the standard error. And then so we're going to run that, and then we've got the standardized residuals, we've got ACF residuals, you've got your p-values for L. Jung box statistics, and then we've got the actual plot. And so you can see that we've got the actual plot. And blue is your prediction, and the red is your predictions plus or minus the error. So that's telling you. So ideally what you want is you want the predictions in blue, because that gives you your standard error. And what I could do, but I'm not going to do it because it takes a really long time to set up the PDQ. But what I could do, I did it. I said print pred, and then so these are the predictions for the next 10 years right here. So that concludes this video. And at the bottom, I have a note saying thank you for studying with me. So I made sure that I stopped the video in places where you can pause the video, and then when you pause the video, you can copy the code and use the code. And I think setting up the PDQ order is really important because it's hard to find that code. I had the code in Python, and then I asked Copilot to convert the code to R. And so the code for setting up the order is very important. But you can always stop the video in the places that I have the code and copy the code. So I hope that you find this video useful. If you like my video, please like and subscribe. And I look forward to making more R-related content for you soon.